Hi, my name is Elio Damaggio, and today I'm going to present the talk Connecting Your Devices to the Azure IoT Suite. First of all, Azure IoT Suite makes it easy to securely connect millions of devices to your application backend. And this can be done to receive telemetry and to send commands. Not only that, but Azure IoT Suite is designed for multi-platform devices and multi-platform backends. Before we start going deeper in the agenda, let's start and see what the talk is going to be about. We're going to start by introducing device connectivity in the Azure IoT Suite. Then we're going to talk about device identity and provisioning. And then we're going to go on to device-to-cloud and cloud-to-device messages. Then we're going to talk about gateway connectivity and monitoring this connectivity, which is very important. So let's assume that you have lots of devices, and they can be of many kinds. They can be IP capable, so able to connect to the internet directly, or they can be low power embedded devices that can only connect to personal area networks, things like Zigbee or co-op protocols. The IP-capable devices can connect directly to Azure IoT Suite through this component that's called IoT Hub that we're going to explore much more deeply in this talk, or through a cloud protocol gateway in case that that these devices do not interface with a protocol that is natively supported by IoT Hub. Other devices that cannot connect to an IP network might need to have other devices to mediate for them. Those devices are called field gateways, and they're basically used to mediate the communications between low power and non-IP capable devices with the cloud. On the backend side, the IoT Hub allows your event processing and insight components to receive telemetry and messages from your devices. Components such as Azure Stream Analytics or Apache Storm can allow you to process this data at very high scale. Your application runtime logic that might want to send commands and receive requests from devices, and that can also use the IoT Hub to mediate these commands and these request reply patterns. Finally, you're going to have in your backend a device provisioning and management component that will make sure that all your devices that you have in the field are correctly configured and work as expected. In this talk, we're going to specifically focus on how the devices can connect to IoT Hub and how all the parts of your backend can interact with IoT Hub to communicate with the devices. There are, of course, many aspects to connectivity. The first one is functionality. This can be very simple messages like device to cloud or cloud to devices, but it can also include other form of communications like bulk uploads and downloads of files. There are also many kind of securities that are of security concerns that are important in addressing device connectivity, and they can be the security of the device, of the cloud, of the channel. In this specific talk, we're just going to talk about granting access rights to the devices, to the IoT suite, and not for the IoT security end-to-end. There is another talk in Build that talks about IoT security in an end-to-end aspect. Please look at that talk. Another aspect that is very important is monitoring. In many IoT solutions, devices cannot be reached besides using network communications. In those cases, any form of malfunction of the communication effectively prevents troubleshooting and management of the devices. This is why the Azure IoT Suite and in the IoT Hub component allows you to have to monitor the connectivity of the device and receive feedbacks and events on what is happening in all those channels for all of your devices. Finally, and also not less important than anything else, are reach and customization. Azure IoT Suite has as a goal to be able to connect to all possible devices, be them being like very, very small, low power embedded devices running real-time OSs, to Linux devices, Windows devices, and so on. Also, we want to enable the use of any protocol that you might be using. We are aware that IoT solutions are most often brownfield, and there is already lots of investment in existing network protocols. Finally, we also want to support custom authentication schemes. So not only ones that are supported first as first class, but will enable any authentication schemes that you already have implemented or are required to use in your solution. Let's go on and talk a little bit deeper about IoT Hub. First, IoT Hub is designed for IoT. It is a service that it is a component of IoT Suite that allows you to connect millions of devices to a partition backend. This is to provide cloud-scale communications, device to cloud and cloud to devices in the form of durable messages, providing at least one semantics. This allows you and your application to focus on the actual business logic and not on complicated retry and reliability patterns. IoT Hub supports a high-density gateway that allows millions of simultaneously connected devices. This is very important when you actually have lots of devices and you need them to be reachable at any point in time. IoT Hub supports cloud-facing feedback regarding delivery receipts and expiration of messages, and also for any device communication errors. This is fundamental in IoT solutions. IoT Hub also supports per-device authentication, allowing each device a specific identity and a set of security credentials. Not only that, but each device actually can multiplex all the connections to IoT Hub on the same connection. This is critical to save resources both on the device side and on the cloud side. And it is, of course, multi-protocol and multi-platform. Let's talk about the endpoints that IoT Hub exposes. On the device side, each device has a couple of endpoints, one to send and one to receive messages. Of course, gateways which can represent multiple devices and can operate over multiple of these endpoints, again on a single multiplex connection. On the backend side, IoT Hub has a receive endpoint for device to cloud messages, which is usually used by your event processing component and your device runtime logic. Your device runtime logic also interacts with the cloud to device send endpoint, which allows you to send messages to the devices, and also to your feedback and monitoring endpoint to make sure that the messages correctly arrive and implement retry logic where that is required. Finally, your backend also will have a device provisioning and management component, which will definitely interact with IoT Hub to keep the device identity in sync and up to date with your master device registry. An IoT Hub also exposes an IoT Hub management endpoint, which allows you to configure parameters for performance, security, and functionality of the IoT Hub component in your solution. Of course, the Azure IoT Hub suite, the Azure IoT suite will provide SDKs for all of these endpoints that will come in two different flavors. There will be the device-facing SDKs that are aimed at devices and field gateways, which will support many platforms and many languages. On the other side, we'll have an SDK that is specific in functionalities for your backend and for cloud gateways that will again be available in multiple languages. During this talk, we're going to talk about a sample scenario. We will have a simulated wind turbine that emits telemetry every second. This simulated wind turbine will be simulating a state machine of a turbine that is started or stopped, and of course we're going to be able to command this turbine from the cloud. The first step is to provision the device. There will be a portal that will update master the device registry with the identity of a new turbine, and will also update the IoT Hub, effectively enabling connectivity for that simulated device. The device then will be able to connect to IoT Hub and emit telemetry every second. On the back end, an event processor will use the receive endpoint to process those telemetry messages and to update the telemetry on the portal. Finally, the portal will also be able to send commands to start and stop the turbine through IoT Hub to each specific turbine. The simulated device will execute the command and send a response through the device-to-cloud pipeline to the event processor, which will then update the command store, keeping track of exactly what happened. Let's see this demo in action. I have here a very simple portal where there are already two devices provisioned, and you can also see the history of commands that those devices had. Let's create a new device. I can create a device with any device ID, and what this will do, it will provision a device inside a device registry, in this case a DocDB collection, and then create that identity inside IoT Hub. Not only that, IoT Hub will in turn generate a key that I will be using to connect the simulated the device as this device. Now, I also have an event processor already started here. These are messages that I was sending a few minutes ago, and then we can now start a device, a simulated turbine, that will then start emitting telemetry about wind speed, blade tip speed, torque, and output power. The event processor should then be able to see to receive these messages, like we see here, and in my portal, the telemetry would be updated. What happens now is that I can send a command to the new turbine to stop. Actually, this was the old turbine. To the old turbine to stop. What I'm going to do here, I'm going to click Stop Turbine. I should have received the stop. What's going to happen now is that in my the stats should basically reflect the fact that this turbine is stopped, and my command store should actually have a command history right now for this stop command. Now let's wait for the turbine to actually stop. Now we see that it stopped, and what has happened is that the device sent a response for that command that should appear, that appeared here in my command store. Of course, we can also create, the whole idea is to have lots of these devices, so we can of course start another turbine, which will of course appear in here. We will look at the code snippets for these projects on how to create and send these commands later in the talk. Well, let's talk now about device provisioning. That is the first and very important step of creating an IoT solution using a IoT suite. Device provisioning is a term that in this talk is used to represent making devices known to your system. There are usually many subsystems that are involved. We talked about a device registry, an IoT hub, but there could also be many others. There could be ERPs and other systems that you have in your full solution. Not only that, the concept of device identity that we're going to use in this talk is related to the identity of a connectivity from a connectivity perspective. In your solution, usually device identity can be a much more complex concept. There could be solutions that have composite devices. Think about an airplane that has like many different subcomponents, all with different IDs and with different communication sub-devices. Also, there are many concerns. Some you might have to map the different form of identities depending on legal or procedural requirements. To explain better this concept, we will have here an example of a sample provisioning flow, just to make sure to explain how this might be represented in a real system. A device could be provisioned at a manufacturing state into the system. The first time that it connects, it could be it is bootstrapped to its specific regional data center. This is very common when the manufacturing is a global operation and there are many different regional data centers that have to manage the individual devices. The point is that at manufacturing time, the device might not be already associated to a specific region. Not only that, as a result of a customer interaction, then the device is actually activated and allowed to connect to the system. As a result of some events that could be related to security or other reasons, it could also be activated and finally deprovisioned. All of these steps are and the various functionality that you want to enable at any point of your provisioning flow are very much application dependent and touch many systems. In this specific talk, we're just going to focus on the ones that are relevant for connectivity. And there are basically two main components. One is the IoT hub that is used for access and communication. The other one is the device registry that is used for querying and discovering your devices based on application-specific parameters. Think about the specific plant ID of a wind turbine or region or model number, so on and so forth. On top of all of those systems, the provisioning process is driven by provisioning orchestration, which can use an Azure IoT Suite extensible set of provisioning APIs, which help for the coordination between IoT Hub and your device registry. But in the end, is very much a custom process of your own application. Let's move now to the device identity concept in IoT Hub. The important part is to understand is that IoT Hub does maintain an identity registry that contains per-device security materials, which are, of course, used to grant access to the individual devices. It does allow individual device blocking, so you can enable or disable each in individual devices. One thing that is very important is that it does not allow generic queries. So if you, most likely, you will have to have a master device registry implemented in your solution. That is the authoritative store of the existence of a specific device identity. The identity registry effectively enables authenticated communications and is used, of course, to ensure the identity of the devices that receive the cloud-to-device messages. And also, IoT Hub does label all the incoming messages with the authentication method that was used to send that message, and of course the device ID that was used to send that message. In this way, you have full control on the authentication aspects of your solution. Also, Azure IoT Suite wants to support as much as possible custom authentication schemes. We will have, you will be able to store your device identity in Azure Active Directory, and also we allow the use of a master key to connect to IoT Hub in case you want to implement your own completely custom authentication scheme. Let us look now in the demo solution how the identity registry was used to implement the wind turbine provisioning. Here in Visual Studio, we had a class, in my solution, we had a class called Device Manager. And in this, I have, of course, my device registry that is implemented in DocDB, and I have here my credentials for DocDB. And I also have my IoT Hub connection string that is used to connect to my IoT Hub. Then, when a new device is provisioned, I invoke this provision device method, which checks if a turbine exists. It inserts the device in the device registry first, and second, it inserts it in IoT Hub. You see here how it is very easy to create a new device inside an IoT Hub. What happens is that this is already created in an enabled state, which means that it's allowed to connect. What I can also do is that, of course, I can create one that is disabled in case my provisioning flows requires a multi-step activation process. Also, I can also create a specific key. A specific key in this way. So I do not let IoT Hub create my my keys. In this version, we're only supporting a symmetric key, but we will support many different methods for of per device authentication. So in this way, I will be able to create a new symmetric key for my device with a primary key, and of course, in order to do key rolling, a secondary key as well. Now, notice that I create the device in the device registry first, and then in the identity registry. This is important because you do not want to have devices in the identity registry that you're not keeping track of somewhere else. There are many ways to make these two operations transactional. You can keep track of the state inside your device registry. You can use workflow frameworks such as the durable task framework that runs on top of Azure Service Bus. But the idea is that once a device is in the IoT Hub registry, in the IoT Hub identity registry, you have to keep, can only be queried by device ID. Of course, same idea for the provisioning. Notice again that I remove it before from the identity registry and then from the docdb in case that if something happens, I'm not maintaining an activated device inside the identity registry with a potential security hole. Also notice that to retrieve the key from the identity registry is just like a very, very simple call of get device with the device ID, and that's what happened from the portal when I clicked get show key. Okay. Okay. Let's talk now about the device-to-cloud messages. Those are sent from the device send endpoint and received from the backend receive endpoints. The device endpoint is used supports AMQP and HTTPS protocol, and the server-side endpoint supports AMQP protocols. Of course, we'll provide SDKs for both of those endpoints. These messages are the ones that are used to send the telemetry in the example that we showed. This receive endpoints is completely compatible with event hubs, so it does support a partition receiver and client-side checkpointing. All the integrations with Azure Stream Analytics and HD Insight Storm and so on continue to work, and any receiver that you have working with event hubs is going to work with IoT Hub as well. IoT Hub also has some extra services in addition to Event Hub for device-to-cloud messages. It does support millions of simultaneously connected the devices, all of them sending telemetry. It does support per-device authentication, and it supports connection multiplexing on the device side for your the cloud-to-device and device-to-cloud traffic, and also across multiple devices for gateway scenarios. In the sample, what happens is that the simulated devices simulates telemetry values and sends telemetry messages every second. An event processor that is implemented with the event processor host then receives these messages and publishes the state on the telemetry portal. Of course, any other way to receive messages from Event Hub can be used, such as Azure Stream Analytics or HD Insight Storm. Not only that, after this could be the start. This is the start of your event processing pipeline. So the data could go in storage or in analytics pipeline or anything that you want to do with this data. The last step is, of course, the telemetry that shows the last telemetry values for each turbine. Let's look at the code of how this was implemented in the demo. First, this is the turbine simulator. Let's start here with the start simulation method, which gives like a high-level overview of what is happening here. First, we create a device client class, and this is a class that connects to the IoT Hub using the hub name, the turbine ID, and the turbine key. Then there is a simulation loop that starts. There is a send telemetry thread that sends every second, and there is of course a receive loop that is receiving 4 commands. Also, I want to say that while this code is in C#, mostly for clarity during the presentation, I will show later in the talk the snippets on how to do these operations with our C SDK. So the simulation loop basically updates the state machine transition and then actually performs the simulation step that updates all my state variables regarding wind speed and torque and output power, so on and so forth. Let's look on the on the send telemetry thread. This is a very, very simple loop that happens every second. A new telemetry message is created. Here I label the message with the turbine ID, with the timestamp, wind speed, blade tape speed, so on and so forth. And then I create a new message just by encoding this object in JSON. Of course, the message can include any byte array body, so you can use any form of encoding that you want to that is important, that fits best your solution. Then you just invoke the send event on your device client. On the receiving end, I have an event processor host. You see here I just have an event hub connection string. This was an already existing event processor host, and I was able to reuse the code as is in IoT Hub. I create my event processor host, giving my event hub and storage account. This is the same thing that you could do with Storm or with Stream Analytics, of course. And then in my process events, I process my events and I get my my messages. Of course, when I have when the message is recognized as a telemetry message, I update my turbine portal graph by sending a call to the portal. Let's move on to cloud-to-device messages. Cloud-to-device messages are sent from the cloud, of course, through the send endpoint and received by the device. The interface on the device side is AMQP and HTTPS, and on the send side is AMQP. A very important characteristics of these messages is that they do support at least one semantics. These messages are durable in order to accommodate for intermittent connected devices, and the device has to acknowledge the receipt. This means that after the message has been received, the device has to explicitly abandon the message in case it wants to receive the message again in the future, or complete it in order for it to be deleted from the queue. This is very important because a device could fail processing the message for whatever reason, and the message will still be there for the message to consume the next time that the device is able to connect or to process it. These devices also have a time to live, and IoT Hub provides receipts for both the receipt of the messages, so the successful completion, or the expiration of them. This allows you to code a very efficient retry logic in your backend. It is very, very common to have a life cycle for commands. So when you send a cloud-to-device message to the device, you use a correlated device-to-cloud messages for the responses, so that your event processor, like we saw earlier, is able to distinguish between a telemetry message and the response of a specific command. Also, you will receive this feedback regarding the successful completion or expiration of the command that allows you to retry the commands if they are if that makes sense for your business logic. Finally, it's usually common to store the command state in a command registry. That allows you to keep track of exactly what happened to each command and what is the state of each of those. In the sample scenario, what happens is that the portal sends the command to an individual turbine through the cloud-to-device send endpoint, and it also stores the command in the command store. The device can accepts the stop and start commands, and it can also reject commands that it's not aware of. This is very important in the case you do support multiple versions of your devices. Not all commands are going to be supported by every device. These commands are also long-running, and when they are completed or rejected, a response is sent through the device-to-cloud send endpoint. The event processor then uses the correlation ID property to filter the responses from the telemetry. In case of the responses, the command is in the command store is updated with the correct outcome. Also, this is like a very simple tracking of the commands. Usually what happens is that you want to have another component of your backend in the form of a worker role, or like your actual device logic handling this this message, and that can happen by putting a message in the service bus topics or queue in order to parallelize this work at high scale. Let's look at how the cloud-to-device messages were sent in the demo solution. Here in the device registry, I have a method called send command, and here the same thing happens compared to the provisioning. I create a command object. I update my my command store, and then I send the command using the service client. The service client uses the IoT Hub connection string to be created, and then creates a new. You can use the send async method to send a command message to a device ID. Notice again that the message can be anything. In this case, is just a JSON document, but it could be any byte array. So if you want to use other serialization frameworks, you're free to do that. Let's look at how the turbine simulator handles this event. The turbine simulator, when it starts a receive loop. This receive loop effectively uses the device client receive async method to wait for commands. This receive async takes time span as input, in this case 5 minutes. That is a timeout. That gives you a chance to do other things when you do not want to have a thread waiting for those commands during the whole time continuously. And also, this allows for a connectivity style where effectively your device is not connected all the time. This is very common on meter connection, where you want your device to wake up every certain amount of time, and then receive the messages and send telemetry and then disconnect. The received body is deserialized, and of course here, if something goes wrong with the deserialization, I have to handle that condition, and I set the current command with the command. When this happens, I complete the message. This effectively says, well, this effectively tells the IoT Hub that this message was successfully processed. Now, what happens is that since this is a long-running process, when the start or the stop operation finishes, this method called respond to command is invoked by the simulator. And in this case, what I do, I just use send event to send the command response, which is effectively an updated command object. Notice how the command response has a correlation ID that is equal to the command ID. This is required to make sure that this response is correlated on the back end with the correct command. In the event processor now, I'm using this correlation ID property to understand if this is a command outcome or if it's a telemetry message. And if it's a command outcome, in this case, I call this method handle command response. Like we said, this can write something in the store. It could trigger a command lifecycle flow. It could send a message in a service bus topic or queue to parallelize this work in other ways. In case you're using Stream Analytics or Storm, the pattern would be exactly the same. I said before that we were gonna show the snippets of how to do send and receives from C. In this case, we see here how a snippet of our C SDK on how to receive callbacks. Here, like, it's very easy. You create an IoT Hub client, and then you can set a notification callback, which is effectively your receive. Inside your receive notification callback, you are effectively able to receive messages and to operate on them. It is inside this method that you will be required to complete or abandon those messages. After you have your IoT Hub client, you can, of course, send telemetry message. In here, you see that there is a receive confirmation callback, which calls you back when you're actually finished sending all the telemetry events. This is important, again, in case of intermittent connections, where in case of intermittently connected devices, where you want to close the connection, and when you're done sending the telemetry, this makes sure that everything that you actually sent has actually been acknowledged by the backend before you sever the connection. Let's now talk about cloud and field gateways. The use cases for cloud and field gateways are mostly protocol translation or custom authentication. This is, of course, besides some specific application logic that you want to perform on the field in your field gateway. We see, for instance, here that a cloud gateway could offer like protocol translations from between MQTT and AMQP on talking to IoT Hub, or also like any other custom protocol that you might have in your own IoT solution. Field gateways, on the other hand, also allows you to interface with devices that are not IP capable. They could be devices that have protocol that run on non-IP networks, such as Zigbee, or protocols that are not suited or designed for the public internet, such as CoAP. The IoT Hub capabilities for gateways allows you to build cloud gateways and field gateways in a very easy way. First, we allow connection multiplexing for multiple devices. This effectively means that many devices connecting to a cloud gateway could still flow through a same connection from the cloud gateway to IoT Hub, still maintaining their own identity. Also, the Azure IoT Suite will provide you with an extensible, already developed MQTT cloud gateway that you're able to deploy and use in your own solutions. There are a couple of patterns that I want to talk about regarding gateways. The first one is transparent versus opaque gateways. A transparent gateway is a gateway where the device identities are flowing through the gateway. So the IoT Hub is aware that there are like multiple devices connecting through that gateway, and each one of those can effectively have their own specific identity. In this case, IoT Hub can individually authenticate those devices and then, of course, label incoming messages and handle the access control of those specific devices by also being able to enable and disable them individually. An opaque gateway, on the other hand, is a gateway where it's a gateway that effectively is masking its downstream devices to IoT Hub. So IoT Hub is only aware of the field gateway identity, and the identity of the other the devices that are connected through the gateway are managed at the application level. This case is, of course, also support, but the IoT Hub then cannot provide services for those downstream devices. They cannot be individually enabled or disabled, and of course the incoming messages cannot be labeled. And another big distinctions is between pull gateways and push gateways. A push gateway is a gateway that has to translate between the protocol pattern that IoT Hub exposes, which the device always connects to the hub, even to receive messages, and instead through the pattern of single devices that are acting as little servers. For many personal area network devices, a very common pattern is to have them act as little servers, so that they receive calls when they want to be contacted. In this case, the field gateway has effectively to mediate between these two patterns, which effectively means that it has to know in advance which devices it's listening for, and it is responsible for with respect to the IoT Hub. Monitoring the device connectivity is the final topic of this presentation, and it is very important for IoT solutions. IoT solutions most often cannot reach the devices besides network connectivity. In this case, anything that is affecting the device connectivity is a blocking error. For this reason, IoT Hub does expose a specific endpoint to relay to the backend all the things that it knows regarding connectivity, not only successful cases, but also error conditions. So events are going to be generated regarding the device connections and disconnections, also when they're failing. So for a connection, you will know if a device is trying to connect but with wrong credentials or with the wrong protocol version, or for disconnection events, you will know if it has been a clean disconnection or if the connection was interrupted and timed out. Same things for device errors. A device might have like errors trying to send telemetry or to receive commands, depending on maybe for wrong versions of firmware or component software. This is again an Event Hub compatible endpoint. This endpoint allows you to create very complex logic regarding device connectivity without having to maintain a high-scale gateway that the IoT Hub is doing for you. So, for instance, an example is complex device blocking logic. Let's assume that you want to disable a device if it tries to authenticate many times with the wrong credentials. In this case, you could have an Azure Stream Analytics job evaluating the number of failed connection attempts per device, and if something and if that the number is greater than something like 10 in the last 2 hours, you can raise an alarm. This alarm could go inside IoT Hub and disable the device, or let somebody know that device might have a wrong key, maybe a key rolling that was not executed properly, or there's a malicious attack happening. This kind of complex logic can happen on any device error and any connection and disconnection events, because we're going to let those informations available to you. Finally, I want to direct you to watch other IoT-related sessions in Build. One is the Microsoft Vision for IoT. There is a session regarding best practices for creating IoT solutions with Azure. And finally, the session that I already referenced before is about the security concept for Azure IoT services that talks about security end-to-end and not just related to connectivity. Thank you very much for watching, and enjoy the rest of Build.